Hello, welcome to this lesson in the Chemistry Tutor. Here we're going to conquer one of the most central things that you're going to learn in chemistry, certainly when you're studying the gas laws, and that is the ideal gas law. So here we're going to introduce the ideal gas law as an extension of what you already know, and so by now you probably understand the significance of where we're going, at least from a big picture point of view. First, we started looking at these individual laws like Boyle's law and Charles' law and Avogadro's law. Then we combined them all together and we found something called the combined gas law. And those laws were very useful when you're going from state 1 to state 2. And that means, I have a certain amount of gas, a certain volume, certain pressure, certain temperature, and then I change something. So state 1 was the initial state. I changed the temperature or I changed the pressure, and then I want to know maybe what the volume is or something in the final destination state. So going from state 1 to state 2, those are basically the kind of problems we've been doing so far. But the ideal gas law is kind of is an umbrella over everything we've learned so far. And so when you understand the ideal gas law, you'll be applying it to problems throughout chemistry for a great many type of problems. So in order to understand where it really comes from, remember, so I'll just say up here, recall, something that we learned in the very last section. The combined gas law was P1V1 over N1T1. And we said that no matter what gas you have, if you know its pressure, its volume, the number of moles, and its temperature in Kelvin, and you do this calculation, you're going to get a constant. Right? And this constant was going to be true no matter what combination of variables we have. If you change the pressure, change the volume, then the new temperature or whatever it is that you obtain, if you recalculate this in some other state, you're going to get exactly the same thing. So P2V2 in some other state is N2T2, like this. So that's what this is intended to represent. No matter what state you subject your collection of gases to, if you know the pressure, the volume, the temperature, and the number of moles, and you do this calculation, you're always going to get the same number. But I told you that it didn't really matter what that number was in the previous sections in the combined gas law, because ultimately what we did is we kind of take it out and we make these guys equal to one another, and then we use the relation that we did for the combined gas law. So this was called the combined gas law, and we've already studied that. We've already done problems like that. Okay, but now what we want to do is we want to derive what we call the ideal gas law. So we really want to find this constant. We want to solve for this constant. And what you're going to end up finding is it's going to be called the universal gas constant. Okay, so we're going to call the constant capital R. You'll see that in your chemistry book. We want to call this gas constant R, capital R. Okay, and so the question would be, if I asked you, how would you find what this constant is? How would you be able to do that? How would you be able to calculate it experimentally? If you're trying to calculate the universal gas constant, how would you do it? Well, the one way to do it is basically just to kind of recognize that the universal gas constant R, this thing right here, is equal to PV over NT. So literally, if you go in the laboratory and you know that you have somehow already ahead of time, maybe 1 mole of gas or 2 moles of gas, but if you know what N is, and you know exactly what the temperature is, and if you can measure the pressure of the gas and exactly what the gas's volume is, then if you calculate this thing and put in the numbers and divide it, then the answer you get is, by definition, what we're saying is this constant number called the universal gas constant. Okay? So clearly when you do this experiment, you have a couple of choices. Now, the number of moles is always going to be in moles, okay? And the temperature is always going to be in Kelvin, because in chemistry we use Kelvin temperature. But when we use the pressure, when we stick a pressure in here, we have a couple of choices. We can put the pressure in atmospheres and calculate the universal gas constant. We can do the pressure in torr to get the universal gas constant. So there's a couple of choices. So the bottom line is there's actually more than one value for R, the universal gas constant, but it only depends upon the units that you're working with in your problem. So you need to be careful when using the ideal gas law that you use the proper value of R, the universal gas constant. So I want to write all this stuff down for you to make it really, really easy. So here I'll create a little table, value of R, which we're going to call the universal gas constant. It's really one of the most important constants in chemistry. So we're going to get this value of R, and I'm going to put another another table over here, another column over here, when. You'll understand why I'm doing that in just a second. Okay, so we have a couple of different choices. The universal gas constant R is equal to, I'll just put R, is equal to 0.082058, okay? That's a very small number. And it's equal to this when the units are liters, atmospheres, over mole, and Kelvin. Look at what this is basically saying. It's saying that, hey, if I go and calculate R using this equation, if I stick liters in here, that's V on the top. If I stick P in atmospheres, and then if I use N in moles, and if I put T in Kelvin, then this is the number I use. So basically, in your problems, you're going to use this value of R when P is in atmospheres. And then you're going to, of course, use liters, moles, and Kelvin. So if I'm doing a ideal gas law problem, which you're going to do a ton of them, and you're dealing with liters and atmospheres and mole and Kelvin, then R is always going to take on 0.082058. Okay? But as you know, sometimes in chemistry, you have different units, depending on what the problem is. So you have another choice for R. Sometimes you might end up needing to use the value of 62.364. Okay, how would this come about? You would use this value when the units of R would be liters, torr, moles, and Kelvin. So you see what I'm doing here? I told you to calculate R, all you need to do is know the gas pressure, the volume, the number of moles, and Kelvin. So this is what I'm trying to tell you. This guy in pink here, this is the units of R. Okay, so because it follows straight from this equation. So the value of R is this when you're using liters, atmosphere, moles, and Kelvin. And the value of R is this when you're using liters, torr, mole, and Kelvin. So basically you use this value of R when the pressure is in torr. And of course then you're also using liters, mole, and Kelvin. This is probably the number one thing I can stress to you to make sure that you understand is that when you're doing your problems, do not gloss over the units that you have. These types of problems with the ideal gas law, you have to know what units you're using so that you can use the right value of R. Because you can see right away if I stick R for this value and if I stick R for this value incorrectly, I'm going to get the completely wrong answer if I use the ideal gas law with the incorrect value of R. Okay? Now there's one other value of R that you'll probably see thrown around your book. I'm going to put it here for completeness. You don't use it too much, at least in introductory chemistry, but you do see it occasionally and you use it an awful lot in physics. So I want to make sure we're being complete here. R can also take the following value, 8.3145. Now this is going to blow your mind a little bit. The units of R in this case, if you use this guy, is going to be joules on the top, which is a unit of energy that we learn in physics class. And on the bottom, you still have mole and Kelvin, okay? So the question is, when would you ever use this guy? Well, you would use it when the P, the pressure, is in pascals, okay? And you would also need to use it when the volume is in cubic meters. And then, of course, you're still using moles and Kelvin over here. Okay, so this is the complete table. These are the there are other units of R that you could use. I mean, for instance, there's other units of pressure out there that we've talked about in the very beginning, right? So you can use different values of R if you're using different system of pressure that we've talked about, before. But certainly these are the most common ones. Almost always you're going to use liters, atmospheres, moles, and Kelvin whenever you're dealing with these kinds of problems, in which case you use this value of R. And these units here are the units of R, okay? Also, if you're using P and torr, then you'll be dealing with liters, torr, moles, and Kelvin. You would use this value of R. And then the question is, when do you use this guy? Well, if you're using P for the pressure in pascals, remember that unit we talked about. And also, this is not an or, this is if you're using P in pascals and V in cubic meters, because remember, liters is a unit of volume, but cubic meters is also a unit of volume as well in the SI system. Then if this is the pressure in pascals, the volume in cubic meters, and using, of course, mole and Kelvin, then you end up with this value of R. Now, the number one question that we get when we see something like this, students say, Well, if you're using P in pascals and V in cubic meters, how in the heck do you get this volume? You see, for these I taught you, hey, it's really easy. You just stick atmospheres in here, and liters in here, and moles in here, and Kelvin here. This is the unit for R. But this looks a little bit weird because I'm putting pascals. I'm telling you, if you put pascals for pressure, and if you put cubic meters for volume, and if you use moles on the bottom and Kelvin on the bottom, somehow you get joules on the top. And you have this weird number. So the question is, how does that happen? Most books are not going to explain it to you. I'm going to take just a few seconds to explain it to you because I like you to understand everything, at least the basic idea of where it comes from. So we're saying that the unit that you can get for R is joules over moles on the bottom and Kelvin. And we're saying that you get this when you plug in P is in pascals, and V is in cubic meters, and of course you have moles and Kelvin. That really never changes. You're almost always using that. But somehow when you stick this into there, you get joules, okay? So the question is, how do you calculate R? Remember, we wrote it down right here. The universal gas constant R is PV over NT. So we'll have universal gas constant R, PV over NT, okay? So if P is in pascals, let's put pascals here. For pressure. For V, let's put cubic meters. So we're just sticking the units in here, and then we have N and T. So we have moles and Kelvin, just like we always do. But if you remember back from the very beginning of chemistry, we looked at the definition of what a pascal was. Remember, pressure in its fundamental form is force per unit area. And the base unit of that in the SI system is newtons per square meter, and we just renamed that to be a pascal. So the pascal is really just a newton per square meter. That is what a pascal is. So we'll just substitute it there. And then you still have cubic meters up here, and then on the bottom you still have moles and Kelvin. Okay. So what do you have here? We have square meters on the bottom, and we have cubic meters on the top. So this cancels, both of these m's cancel with two of these m's, so you just have one m on the top. So what you're going to end up having here is a newton times a meter on the top, and a mole times a Kelvin on the bottom. Because both of these meters cancel with two of the three of these, leaving one on the top. So you still have newton times meter, and you have mole Kelvin. So the question is, you would think that the universal gas constant R should be, if we're using these units, it should be a newton times meter divided by mole Kelvin. And the truth is, that really is the units that we really have here. But if you think about this for a second, this is a unit of force, and this is a unit of distance. We have a unit of force on the top times a unit of distance. Force times distance. Does that sound familiar? Force times distance. What equals force times distance? If you remember back to physics, that you've, I'm sure, taken at some point in your life, we define work to be force times distance. Force is always measured in newtons in physics or in chemistry, and distance is always measured in meters. But we know that when we multiply force times distance, newton times meters, we rename that in physics to be the unit that we call a joule, because work is always measured in joule. Joule is a unit of energy. And work is the ability to exert some energy and to influence a system somehow. So the bottom line is, when we put all of these units in here, we cancel everything, we get a newton times a meter on the top. But we know from other science courses that newton times meter is just what we call a joule. So the universal gas constant would then be a joule over mole Kelvin. All right? So the bottom line is, I'm just showing you this to show you how you can end up with a unit of energy on top. It seems a little bit weird. And then the secondary question is, why would you ever use this universal gas constant? Well, the truth is, in chemistry, we don't use it too much, at least in introductory chemistry. But when you get into more advanced chemistry and you start dealing with the kinetic theory and you start talking about the energy of particles and how much kinetic energy they have, which we'll be talking about a lot later, it's nice sometimes to use a unit of the universal gas constant that has units of energy in there. Because sometimes you'll be using pressure in pascals and volume in cubic meters, and you'll be using the universal gas constant in terms of R that has units of energy when we're talking about particles of energy, gas particles of energy and things. So you use it sometimes in more advanced chemistry, and you use it a whole lot more in physics, because in physics we love to work with energy. And so this version of R has that built into the units. But I don't want you to lose sight of the fact, and I think a lot of books do this, I don't want you to lose sight of the fact that no matter if you use this version of R, or this version of R, or this version of R, it's really all the same thing. These values of R, they're all exactly the same thing. They're just the ratio of PV divided by NT for whatever gas you have. The only reason we have different numbers here is because sometimes you might use different units in your problem. So you have to be cognizant of that there. All right, so now we want to come to the punchline of all of this. We've talked quite a bit about units and the universal gas constant, all that stuff. But the reason that we're doing all this stuff is because, remember, we just wrote down a second ago, the universal gas constant is PV over NT. I just wrote that down a second ago. But usually you don't write this typically like this. We write the ideal gas law as follows. We multiply both sides of this equation by N times T, and so we'll have PV on one side by itself. So you have PV is equal to nRT. This is how you write what we call the ideal gas law. Ideal gas law. And it's so important, I'm going to circle it, because the super important things, of course, I like to circle so that you know. This is one of the most fundamental equations in all of chemistry, and all of physics, actually. So you need to make sure you understand that. PV is equal to nRT. It kind of rolls off your tongue. PV, nRT, PV, nRT. Just kind of say it over and over again. You won't even have to remember it or memorize it, because it'll be in your head. The only thing you need to be really aware of is that when you're using this equation, and we'll do problems, the value that you choose to put into R has to be consistent with the units you have. In other words, if I'm using a pressure in atmospheres, and then liters for volume, and then mole and Kelvin, this value of R has to be the value of R that includes liters, atmospheres, moles, and Kelvin. So I'm going to put this value of R into that equation. If, however, I'm dealing with torr, liter, mole, and Kelvin in my particular experiment, then I'm going to put a value of R of 62.364 into this equation. Now, we're going to do actual problems with this in the next section, of course. But this type of equation is very powerful. It's an equation of state, okay? It lets you calculate the state of the gas. In other words, whereas before, if you think about it, the combined gas law, which looks very similar to this, the combined gas law was set up so that I can go from state 1 to state 2 of the gas, and I can calculate the new parameters in state 2. Maybe the new volume, maybe the new temperature, maybe the new pressure, something like that with the gas. But there is no going from state 1 to state 2 here. This is just the current state of the gas. PV is equal to nRT. So what it means is, if I tell you, hey, I've got an ideal gas, and I know the pressure is 2 atmospheres, and I know the temperature is 50 Kelvin, and I have 3 moles of that gas, then that's all I need to know. If I really know how the pressure is behaving, and I know I have so many moles of gas, and I know the temperature is like 50 Kelvin or whatever, and the universal gas constant is a constant, I know what that is, then I'm always able to solve for the volume of that gas. So it lets me complete the calculation for the current state of the gas. That's why it's called an equation of state, okay? So just another example, if I know the pressure, 2 atmospheres, the volume is 3 liters, and I know the temperature of the gas is 69 Kelvin, then knowing the universal gas law there, I plug everything in, I can figure out how many moles of the gas has to be there, because this equation of state governs any ideal gas. Now keep in mind, though, that ideal gases don't really exist. And we haven't really talked about what makes an ideal gas ideal, but the bottom line is there's a lot of assumptions that go into ideal gases that make them basically not real. And we'll list a couple of them here in a second, but just to kind of make sure you understand and on the same page with me, an ideal gas, because this is, by the way, the ideal gas law, so we should probably tell you basically what an ideal gas is. It's a hypothetical gas. And the very definition of what an ideal gas is that it obeys PV is equal to nRT perfectly. That is the exact definition of what an ideal gas is. So you might, if you're on a test and the teacher says, hey, what's an ideal gas? The first answer you should put down is it obeys PV is equal to nRT perfectly. Because if I really take a tank of oxygen and I measure its temperature and I measure its pressure and I measure its volume and I know how many moles I have and I stick it in here, it's not going to be perfect. It's going to be very close, but it's not going to be perfect. Because real gases have collisions between molecules. collisions between the container and the molecules. And all those collisions, they're not perfect collisions in a real gas. You lose a little bit of energy in those collisions. So when a gas molecule slams against the side of the container, it gives some of its energy to the container. Just by the fact that it's interacting with it and it's bouncing off of it. But in an ideal gas, we pretend all of the collisions are perfect and we don't lose any energy anywhere in any of the collisions. Okay, that's one of the main differences. But in a real gas, collisions deliver energy to the tank and to the surrounding environment. And so PV as nRT is not perfect, but it's very close, especially for typical work that doesn't require, super precision. But as you get farther in chemistry, you will learn how to make modifications to PV nRT to obtain more accurate gas law, a more accurate gas law that will obey real gases, okay? So the final thing that I want to talk about in this lesson is a note on the units. Remember, we said the units of R, the universal gas constant. The first unit we talked about was liters, atmospheres, mole, and Kelvin. And I wrote it like this because it was very easy, because remember, I introduced it and said this is how we find our PV over NT. So writing it like this exactly lets you visualize how the units flow into that and why we get these values of R. Okay? But in your book, you might see this unit, you may see as something like this. You might see it as, I'll just change color here. You might see it as liters, atmospheres, mole with a little -1 up there, and Kelvin with a -1 up there. This unit that you see here is exactly the same as this one. I just want to point this out to you because some students, they see this and these little -1s like really worry them and freak them out a little bit, and they're, well, what does that mean? Remember from algebra, anytime you have a -1, it's like moving this thing to the denominator there. So remember, for instance, from algebra, you might have x to the -1 power. That is exactly the same thing as 1 over x to the 1 power. That's what that means. When you have a negative exponent, it just means you move it to the denominator with the same power. So by having mole to the -1, it's the same thing as saying that moles is in the denominator with the power of 1, which it is. And Kelvin, having a -1, means Kelvin is in the denominator with a power of 1 here. The reason books write it like this is because it takes up less space. Because I can say liter, atmosphere, mole, -1, Kelvin, -1. I don't have to write a fraction all the time. Okay, so similarly, you might see liter, torr, mole, Kelvin. This is exactly the same thing as liter, torr, mole, -1, Kelvin, -1. And exactly the same thing you might see for that unit that has joules on the top, joule, mole, Kelvin on the bottom. You might see that written as joule, mole, Kelvin, like that. So don't worry about those things. Don't worry about those things. And then the conclusion of this lesson, I just want to point out something. I mentioned this a few minutes ago, but I just want to kind of close the section and leave you with this last thought before we go solve problems. Some students look at the combined gas law and they look at the ideal gas law and they look really similar. So they're not quite sure what the difference really is between them. Okay? The combined gas law is the one that we've already used before. Okay? That's when you have P1V1 over N1T1 is equal to another state, P2V2 over N2T2. Okay? When you have a situation when you have a gas with some parameters, PV, N, and T, and you move that gas to a different state, you might change the pressure, change the temperature, whatever, and you want to calculate the new volume or something. Moving from state 1 to state 2, you would typically use this because it's set up easily for that, and you don't even need a universal gas constant for these problems. Remember when we did the combined gas law problems, we never used the value of R. We didn't even know what it was then. So you don't need a value of R for those problems, okay? And when you're doing those problems, you can use any units of pressure and volume that you want. You should still probably use Kelvin here, but for pressure and volume, you can use whatever units you want, and you just need to remember that to be consistent between your units from state 1 to state 2. So the combined gas law is very useful when you're going from a gas from state 1 to state 2 and you want to know what's going to change over there. Okay? The universal, or I should say the ideal gas law, is used for a different kind of problem entirely. You're not typically going from state 1 to state 2. You just have a gas in some state and you want to calculate its volume. So I might know the temperature, the pressure and the number of moles, and then I need to calculate the volume. So I'm not moving from state 1 to state 2. I just have a gas in a can with a certain volume, a certain pressure, and I want to find its temperature or something like that. So I would use the ideal gas law. And in this case, you need to be very careful about what value of R to choose because the units does matter. If I'm using liters, atmospheres, moles, and Kelvin, then I need to use that value of R in there or I'm going to get the completely wrong answer. If I'm using liters, torrs, moles, and Kelvin, then I need to use the other value of R and so on. So you use the ideal gas law and the combined gas law basically for different types of problems. And we've already done the problems for the combined gas law. Now what I'd like you to do is take the knowledge you've learned here, follow me on to the next section. We will do some problems with the ideal gas law, and you'll quickly see how interesting and how useful it is to calculate real problems in chemistry. And once we have this knowledge here, hopefully I've made it simple enough for you, you'll see how easy it is to solve these problems as well. So follow me on to the next section, and we'll work some problems with the ideal gas law right now.